So when we're dealing with rationals, if we think in terms of parent functions, the most basic rational that we can come up with is that one. So a rational function is generally written in a fraction form, and we have a variable in the denominator. Okay? So the most basic one is 1 over x. Now, if you go back to your family functions booklet for a second, if you have that with you, what does the graph of 1 over x look like? What are some significant features about 1 over x? It's probably called the reciprocal function in your booklet. Same kind of thing. Go ahead.
The y value never reaches 0.
The y value never reaches 0. What else? So if y value never reaches 0, what does that look like on my graph?
There's an asymptote.
There's an asymptote at y. If my y value never reaches 0,
Oh, wait, there's no
it's my x-axis. So if the y value is never 0, that means I have a horizontal axis on my x-axis. Okay, what else?
X can never be 0.
X can also never be 0. Why?
Because it's on the denominator.
Because it's in the denominator. If we ever have a denominator that's 0, that means it's undefined. We can't have that. And so we're never going to have an x value that's equal to 0 either. Which means we have a vertical asymptote on the y-axis. Okay, what else? Give me some other clues as to what this graph is going to look like. Casey?
There's like a line in the first quadrant and the third quadrant.
A line?
Like, no, like a curve.
A curve. What Mrs. Gordon loves to call the corner huggers. Okay, now you can get more picky about that in terms of actually getting 1, 1, and -1, -1, and all that, but generally that's what happens. You get these curves that curve into the corner, okay? They are in opposite corners of each other because we have that symmetry with the origin, so this is an odd function. Excuse me, and we have, excuse me, both ends of our curve getting closer and closer and closer to that asymptote. So this end of the curve is getting closer and closer and closer to my vertical asymptote. This end of the curve is going to be coming down and getting closer and closer and closer to my horizontal. And the same thing happens over here. Okay? So in general, we get graphs that look like this. Okay? What we take from this is a more inclusive kind of form that says, if I'm dealing with a rational, it can really be any polynomial function over any other polynomial function. So when you see it written like that, we're still going with the idea that we have a fraction. We're still going with the idea that there is a function on the bottom, so probably there's some x on the bottom. But there's also probably going to be x's on the top because we have this p of x polynomial. But the idea is polynomial over polynomial. Okay? That leads us to the fact that we are most likely going to have some vertical asymptotes. Not always, but most likely. We are most likely going to have some horizontal asymptotes. We are most likely going to see some kind of curving like this in the graph somewhere. But there may be some other stuff as well going on. Okay, so how do we get all of the pieces that we need to get an accurate picture of what our rational function looks like? So what I usually recommend is that you start off with the 4 major characteristics, which is figure out where, if anywhere, you have a vertical asymptote. Figure out where, if anywhere, you have an end behavior asymptote. Figure out where, if anywhere, you have x-intercepts, and figure out where, if anywhere, you have y-intercepts. Okay? You may not have some of those things, but those are the 4 things to consider first. Okay? So, if we... I don't remember which one is what. No, that's not going to do it. Alright, we'll just do it this way. Big eraser. So if we go with what's actually here for our function, we're looking at x plus 4 over x minus 3. I usually would say start with the vertical asymptote because it tends to be easier to find. It's sort of the big deal about rationals, is that there are certain numbers we can't use. And we indicate those values by drawing vertical asymptotes. So what's the number we cannot use? 3. Because in our denominator, we have the expression x minus 3. 3 would be the value of x that would make the denominator 0. That's the value we can't use. So if we can't use 3 here, then that means x being equal to 3 is the equation of the line that's going to be my vertical asymptote. Okay? So there's my x equals 3 line. So your vertical asymptote always comes from what's going to make the denominator equal 0. That's what you're always looking for. In this case, it's a simple linear expression, so it's fairly easy to set that equal to 0 and figure out that 3 is the x value that's going to make that happen. Okay? All right, so then the next thing, I prefer to call this the end behavior asymptote because it's not always just horizontal. Sometimes the end behavior asymptote is a slant asymptote. So the end behavior asymptote is kind of an overall term that takes both of those into account. And the purpose of it is exactly what it sounds like. The purpose of a horizontal or slant asymptote is to tell us what's going to happen at the ends. Okay? So an end behavior asymptote is that funky one, the funky rule, about exponents. Okay? You might remember this from Algebra 2. So there's 3 possibilities when you look at the exponents of your numerator and your denominator. Either the top exponent is smaller than the bottom, the top and the bottom are the same, or the top is bigger than the bottom. Those are your 3 possibilities. Okay? And we often refer to the degree of our numerator being m and the degree of the denominator being n. Whoops. If you look in textbooks, that's usually how they differentiate them. And so we've got these three different possibilities. Either m is smaller than n, m equals n, or m is bigger than n. Okay? So think about what we're saying here. It's not just about learning the rule. Think about what's going on. If the degree in the numerator is smaller than the degree in the denominator, as I increase x's and go bigger and bigger and bigger with x values, which one grows faster, the numerator or the denominator? The denominator, right? If the degree is bigger in the denominator, then my denominator is going to grow at a much faster rate than what my numerator is as my x's get bigger and bigger. Does that make sense? Okay? So now think about this for a second. If you just think about a fraction, and you think about fractions where the denominator is going to get really, 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 really big, what's happening to the overall number?
Smaller.
It's getting really, 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 really small. And it's getting closer and closer and closer and closer to what? 0. So when your top degree is less than the bottom degree, so your denominator is growing faster than your numerator is, you always get a horizontal asymptote of y equals 0. That's just a given. Don't have to figure anything out on those. You just have to recognize that your numerator degree is smaller than your denominator degree. Okay? Now, what if the two degrees are the same? So now how are you going to tell whether one is growing faster or not?
They're going at the same speed. They're going at the same speed.
More or less they're growing at the same speed, right? If it's the same degree, they're essentially growing at the same speed. So what's the only thing that's really going to affect that at all? Any kind of coefficient that you have out here. Okay? So if we call this coefficient A, and we call this coefficient B, then when our degrees are equal, what we're going to get closer and closer to is whatever A over B is. So that's going to be our horizontal asymptote. Okay? Because that A over B is what actually sets up the ratio now. It's not about the degrees are the same. So the comparison of how fast your numerator grows in comparison to your denominator is all about those coefficients. They're going to set up that ratio of numerator to denominator, and that's how you're going to know where your answers are going to get closer and closer and closer to if you get bigger and bigger x's. Okay, so in these two cases, kind of get it in there. In those two cases, we're getting a horizontal asymptote. It's just a matter of, is it going to be at 0 or is it going to be at some other number? In the last case, which one grows faster?
The top one.
The top one, the numerator. Because now m is bigger than n. So our top degree is bigger than our denominator's degree. And so it's going to grow much faster. So in order to know what kind of answers we're going to get from that kind of a fraction, and where our answers are going to be closer and closer and closer to, we have to actually divide p of x by the q of x in order to see how many times bigger is my numerator, and therefore where my answer is going to be going. So in a sense, in this case, you're actually trying to kind of simplify this division that you have going on, right? Because if a rational is written as a fraction and fractions are just a type of division, you've really got division going on here. So in this case where m is bigger than n, we actually have to divide it out and try to get it to not be the fraction or the division anymore and just see what is the answer we get. Now when you do that, you could end up taking a quadratic divided by a linear, right? Or a cubed root divided by a linear, or sorry, cube divided by linear, something like that. If the denominator is linear, you can use synthetic, right? Because the bottom would fit that x minus c form that we have to have in order to use synthetic division. But somehow you need to actually divide this out, and then if you get a remainder when you divide, you don't care. The remainder is just going to get dropped off. Okay, because essentially you end up then with another fraction where if x gets really, really big, it's the denominator that's going to get really, really big, which means the whole remainder is going to get really, really small, and for all intents and purposes, it's not going to make any difference. So whatever answer you get from that division, you drop off the remainder, and that equation now, the graph of that equation becomes the end behavior asymptote. So yes, this is usually where we get our slant asymptotes. Most of the time in high school, we only talk about things that are like, a quadratic divided by a linear. So you end up with a linear that's going to be a straight line, but not a horizontal or vertical line. It's going to be at a slant. That's where the slant asymptote name comes from. But it's possible to take a cubic divided by a linear and end up with a quadratic. So it's actually the parabola that's going to dictate what happens on the ends. I mean, all of that is possible, we just don't usually get to that level in high school. Okay? All right, so what is the situation in this case? How do our degrees compare in this case? And I'll erase all this mess again so we can see what we're dealing with. Okay, so how do our degrees compare here? They're the same. So we're talking about this situation, which means our end behavior asymptote should be what? Should be what? Y equals 1. Thank you. Please, please, please understand that an asymptote is a line. And lines must be communicated by equations, not by single numbers. So if I ask you for an asymptote and you just write down VA 3, EBA 1, you're going to get points taken off. Because you are not telling me the equation for the line that is your asymptote. That's what I need to know. So this is going to be y equals 1. Because my leading coefficient here is 1, my leading coefficient here is 1, and I'm supposed to take a over b, so 1 over 1 will give me 1. Okay, so I can draw that one in. Boom. So my asymptotes now have taken my graph and divided it up into sections. So these are the sections I'm going to be graphing in. Now, in addition to that, I can find the most obvious points first that are going to help me out by finding the intercepts, if they exist. How do I find the x-intercept? Sorry? Okay. Why? Why does it work to plug in 0 for y? Okay, so if you think about what's going on at points that are on the x-axis, these are all points that have a y-coordinate of 0, right? Okay, so if I plug in 0 for y, what is it about that rational expression that's going to happen in order to get an answer of 0?
X has to be -4.
Why?
Because then it'll be 0 over x. 0 over -7 and that's 0.
Okay, so what is it about a rational that has to happen in order to get an answer of 0? The numerator has to be 0. Okay? Provided that you don't end up with 0 in the denominator as well. So we're now looking for values that are going to make the numerator equal to 0. So we're going to say that this is -4 because we need numerator to equal 0. What's going to make that happen? Okay, so an x-intercept at -4 means I'm 1, 2, 3, 4 right there. All right, last but not least, y-intercept. How do we get that? Put x equal to 0. Okay, because similarly, any point that's along our y-axis has an x-coordinate that's 0. So if I just put in 0 for x, what are we left with? -4/3. So you can actually put the zeros in for x and work it out, but what ultimately ends up is constant over constant. Okay, so -4/3. So that puts my y just a little tiny bit lower than, oh, stop that. There we go. A little bit lower than -1. Now, at this point, you've done all the special stuff. You found the asymptotes, you found the intercept points. Now you take a look at it and you go, okay, what can I tell from what I have, and what do I still need to figure out? Can you tell anything about your graph right now just based on what you're seeing?
The bottom left has to be the left curve.
Yeah. So we can tell what's going on down here in this section because I've got 2 points that my graph has to go through. So I'm pretty confident about this one. I'm going to go ahead and draw this one in as best I can. There we go. What am I not so sure about yet?
Where the other side,
Yeah, where anything else is going to go. Is there going to be any graph up here? Why not?
because you already got it.
Right, because if there was, it wouldn't be a function. Right? If I draw something up here as well as down here, then I fail the vertical line test. Okay? So I'm not interested in trying to come up with anything else here. What I'm interested in is what's going to happen over here. Am I going to end up with a graph up in this corner, down in this corner? Where's that going to go? Yes?
Can you just rotate it for 2 points that you already got?
No, not necessarily. Okay? It does work sometimes, but not consistently enough that we can make it a rule. Okay? So you're better off actually just testing a couple points to be sure. Okay? So, here's where we just need to test some points. So we'll make ourselves a little t-chart. Okay? And what would be some good x values
4.
to get me the information I need? Something that's to the right of my asymptote, right? So if my asymptote's at 3, testing something like 4, maybe 5, just get a couple more points there so I know which corner I'm going to end up in and what my graph's going to look like. Okay, 4. 4 plus 4? 8. 4 minus 3? 1. So I end up with 8. So 4, 8. 4, 1, 2, 3, 4, 5, 6, 7, 8. Boom. Okay, how about 5? 5 plus 4? 9. 5 minus 3?
2.
Which is about 4.5. 5, 1, 2, 3, 4.5. Now I have a pretty good idea what this one looks like. And that's your graph. Okay? So, regardless of what kinds of polynomials you have for your numerator and your denominator that make up your rational in the first place, this is the process you can always go through. You're always going to look for your vertical asymptote based on what's going to make your denominator equal to 0. You're always going to find your end behavior asymptote based on comparing degree of numerator and denominator. You're always going to find your x-intercept based on what makes your numerator equal to 0. And you're always going to find your y-intercept based on what happens if I put 0 in for x. Okay? And if you can get those 4 things in place, then figuring out the rest of it should be pretty easy. There shouldn't be a whole lot more work involved. Questions? All right, let's try the next one. Okay, so let's kind of just break this down in pieces. First thing I want you to do is to find the vertical and horizontal asymptotes. Write down what you think your vertical and horizontal asymptote should be for this rational function.
Wait, wasn't this the one that had a typo?
Yeah.
It's just the plus minus is going to be negative. Yeah. Yeah, that plus minus 3 just is meant to be minus 3. All right, who thinks they can tell us the vertical asymptote? Charlene, what do you think?
3, x equals 3,
X equals 3, and x equals -1. Okay, can you tell us how you decided that?
I factored the denominator and found the zeros.
Okay, what would the factors be?
X minus 3 and x plus 1.
So if you're looking at a denominator that is quadratic, then we need to go back to our quadratic methods for figuring out if I set this equal to 0, what are my x values going to be? And since this is one that we can factor, we can find those values by factoring into x minus 3 and x plus 1. And then imagine if I set that equal to 0, what would I have for solutions? +3, -1, that's where my asymptotes are going to be. So x equals 3 is going to put me out here. And x equals -1 should put me right about there. Okay, any questions on that step? Everybody good with that? All right, end behavior asymptote. Anybody think they got this one? Stephen, what do you think? And why do you think that? Because m is less than n. So the degree of my numerator is what? 0. Yep, if there's no x, that means the degree is 0. The degree of my denominator is 2. So if my degree on top is smaller, That automatically means y equals 0 is my end behavior asymptote. That's going to go like that. So at this point, we have taken our graph and we've actually divided it up into 6 sections here. Okay, which is going to help because now we know that only certain sections are going to get graphs and certain sections are not. Okay, but we don't have any points yet to know which sections to go in. So now take a minute and write down what you think the x-intercept and y-intercept should be. Okay, so the asymptotes divide up our graph and sort of tell us where our graph could go. Kind of gives us those sections. You can kind of think of it as fencing parts off, or if you've ever had to share a room with a sibling, maybe you've done this, maybe you've wanted to do this, but putting the masking tape down on the floor and saying, you stay on that side, right? Mr. Gordon has this great story about him and his younger brother and doing that when they were younger. And of course, he gave his brother the side without the door. And so this big funny story about how, you know, Toby was always trying to figure out how to get out of the room because he wasn't supposed to cross over on Mr. Gordon's side. But yeah, it's a pretty funny story. But that's kind of what you're doing. You're sort of laying down the tape and you're saying, here's the sections you get to play in, right? And for the most part, you don't get to cross. Now, I say for the most part because there is one exception to that rule, and we'll talk about that in just a second. But for the most part, this is the tape on the floor. You don't get to cross this tape. You have to play in your little section. Okay? So these points are going to help us figure out which sections we're actually in. So, x-intercept. Stephanie, what do we get for an x-intercept? Undefined, right? Because where do we get the x-intercept from?
Numerator with numerator 0.
Setting the numerator equal to 0. Well, what happens if I say 4 equals 0? They can't, right? So that tells us there is no x-intercept. Whoops, I meant that to be red. Go back, you make that red. There we go, undefined. So we know we're not going to be crossing the x-axis because there is no x-intercept, which kind of makes sense because we got an asymptote there. So that kind of goes hand in hand. But again, not exactly. I'll talk about that in a sec. How about y-intercept? Hagen, what'd you get for a y-intercept?
0 and -4.
So again, we're putting 0 in for x. We're just going to end up with the constants, and that's going to be a 4 over -3. Okay, so I can put that point in. -4/3 again, going to go right about there. Okay, so is there anything I can tell about how to draw this graph right now? There actually is. There's one section I can actually draw at the moment. Yep. Because what happens in between when you have sections like this is that almost always, the sections on the outsides are going to be the corner huggers. Okay? Like what we saw back here, right? The ones that just kind of curve into the corner. But What happens in the middle can be very different. But usually what happens in the middle is one of two things. Either we end up with something that looks an awful lot like a parabola, or we end up with something that looks an awful lot like a cubic. They're not exactly, because there's limits to just how far we can go, but they have those shapes to them. Okay? So, based on the fact that I have a point here, and based on the fact that I cannot cross the x-axis, which shape must be in the middle of this one? An upside-down parabola. Because if it was a right-side-up parabola, I'd be crossing the x-axis. If it was something cubic, I'd be crossing the x-axis. So the only possibility where I have that y-intercept and I cannot cross the x-axis is that it must be some sort of parabola that opens down. Now if you want to be a little more specific, you could maybe put in a 1 here to kind of see just where that sort of vertex-y point should go. Okay, so if I put in 1 real quick, what are we going to get? 1 minus 2 minus 3, a negative 4 over 6. 4, this gives me 6, or negative 6, negative 4 over 6, which simplifies to negative 2/3. So negative 2/3 is going to be right about there. So now I have a pretty decent idea. That's going to do something like that. Okay, so I can draw that piece pretty much just based on what I had. Maybe find one more point just to get that vertex, but pretty much based on what I had, I know that's what that one's going to look like. Okay, yes?
What if there was no horizontal asymptote? How do you figure out which graph it was?
Other points.
Oh.
Yeah, so if you had no horizontal asymptote, actually, okay, so here's a little detour. Having the horizontal asymptote does not necessarily mean you can't cross this line. Okay? This line here in the middle is the tape's on the floor, but I have to get out of the room. So you're going to have to let me cross for 2 steps because I have to get out of the room. Mom's calling me, and if I don't come, she's going to, whoop us both, kind of thing. So yeah, the line's there, but I have to cross it. Okay? Because what does the green represent? End behavior asymptotes. So the green only really affects what's happening on the ends. It does not dictate what happens in the middle. So I am allowed to cross the horizontal asymptote if it's in the middle of the graph. Okay? So it's possible I could have had a cubic here if I didn't have this piece of information. This is the piece of information that's keeping us underneath, because I cannot cross through the x-axis anywhere. I don't have an intercept to do it at. Okay, so it's not just based on the fact that there's an asymptote there. Okay, so if you only have the 1 point and you're still not sure, then you need to just start plugging in some x's to make yourself sure. Where are those other values going to go? Okay. There's something else I was just going to say. Don't remember what it was. Hopefully it'll come back to me. All right. The vertical asymptotes, though, those are like building a new wall in your room, right? Like it's not just tape on the floor that you can kind of, if you've ever had a younger sibling, you know what I'm talking about, right? Okay, that's not this. Vertical asymptotes are like you came in with bricks and mortar and you put up a new wall. Like there is no way your sibling's getting through.
That's what I do.
Okay? I don't suggest that without parent approval, but so there is no way ever that you get to cross a vertical asymptote. But horizontal asymptotes are kind of, it's just the tape on the floor, and I have to go to the bathroom. So do you want to clean up the mess here, or are you going to let me cross? You know, that kind of thing. All right, what's going to happen on the ends now? That's where we don't really have any information. So that's where we're going to have to plot some points. So what would be some good x values to decide what's happening over here on the left side? Negative what? Negative 2. Let's get a couple in there. Negative 3. Okay. And one thing I recommend, because you already factored this, use the factored form. It's easier. Rather than going through, okay, what is that squared? And then I'm going to add that, but it was actually negative. No, just use the factored form. It's easier. All right, so if I put negative 2 in here.
Negative 5.
Negative 5.
Negative
1. So negative 5, negative 1 are 5. And it's 4 over that. So 4/5 at negative 2. Negative 2, 4/5. Muscle negatives. There we go. Okay. How about negative 3? Negative 3 in here. Negative 6. Negative 3 in there. Negative 2. Negative 6 times negative 2. 12 and 4 over 12. 1/3. More or less than 4/5?
Less.
Less. So I got to go a little bit less than over here. Well, stop that. Okay? So once you have 2 points in a section, as far as I'm concerned and as the level of accuracy we're getting to, this is enough. Use those points, draw your corner hugger, boom. Okay, is there going to be anything down here? No. So now we can move over to this section. So what should I test over there? 4 and 5. Okay. So again, 5 in here.
1. Oh,
5 in here.
2.
2. 5 in here. 2 times 6.
12.
Bad morning. 4 over 12.
Somebody needs some coffee.
1/3. All right. So 5 gives me the 1/3. Yeah. Okay. And then 4 here. 4 here. Multiply. 4 over 5. So here we do get that kind of symmetry that you were talking about. It just doesn't always happen.
Why doesn't it always
Because sometimes we get some really funky polynomials going on here. Okay, so it kind of depends on the polynomials you're using, whether it's going to happen or not. And there's no real set rule as to, oh, well, these polynomials act this way, and then these, yeah, it's just easier to put some points in and check it, okay? But don't be surprised when the symmetry shows up. And if it shows up, then you can use it and say, okay, well, it must just be that way then. And this should just pretty much be a reflection of that. There it is. All right, so for all of you who said, I forgot how to get vertical asymptotes, I forgot how to get horizontal asymptotes, I'm not really sure how I'm supposed to get intercepts. Are we all good now? Does that refresh your memory? Any questions still at this point about the rationals? All right, I think it's a good time for a short break. Go ahead and stand up.
That's a good idea.
All right, here's what we're going to do this time. Miss Peterson actually did this with the teachers a couple weeks ago, and it was funny watching these teachers trying to figure it out.
Uh-oh.
Okay, so here's what we're going to do. With your nose, all right, you don't have to touch your nose, but with your nose, you want to make 8s in the air.
What?
Didn't we do that? You did
Just keep doing
and
it.
Right?
You're like,
Do it backwards.
Wrong way. Wait, no.
Do 8s backwards. The other way. Okay, now do infinity signs.
Okay.
oh wait, I was doing it.
Oh, well, I've been doing it.
That's a good sign. Rowing is like a
That's what I did. She said 8s. I went, I'll just make them sideways. That's easier. And then she went, okay, now do infinity. I'm like, dang. Thought I. Okay, doing the other way.
Whoops. Oh, the other way is a lot harder.
Isn't it?
Wow.
It just doesn't seem like it should be that difficult, but all right. Roll your shoulders a little bit. That always feels good. All right, here we go. Let's see some inequalities.
Even real
I'm sure you have.
All right, so the first inequality, number 24, is a quadratic. Okay? Unfortunately, once you get beyond linear inequalities, you cannot just say, oh, let me find the answers as if it was an equation, and then we'll just say all the answers are less than 0. It doesn't work that way. Okay? So, what do we need to do? It was actually really interesting how many people said, oh, well, I got this wrong because I graphed using 2 dimensions instead of 1.
Oh yeah, that's what I did.
That's not necessarily wrong. It's a little bit different than what I had on the answer key, but it's not necessarily wrong. So could someone who did that just explain a little bit what you did? Go ahead, Hunter.
I basically just did, you graph it like an equation and then do the answer that way.
Okay.
So
So,
I did the
as an
parabola,
equation,
and then that's why, yeah, that was on the answer.
that's the answer key, but there were several people that said, oh, I did this with 2 dimensions, so that's why I got it wrong. I want them to explain what they did with 2 dimensions, and then we'll talk about how that relates to what you saw on the answer key. Okay, so keep going. How did you figure out what the parabola was going to look like?
I basically just graphed it like it was x squared plus 4x plus 3 equals 0. So I graphed the parabola and then I just kind of shaded randomly. I wasn't quite sure.
Okay, so tell me how to graph the parabola. What's the parabola going to look like? Where's the vertex? Which way is it opening? How'd you figure all that out?
It's -2. The line of symmetry is -2.
Okay, why?
Oh, wait, no.
Because the x-intercepts are...
It's x equals -2.
Why?
X plus 3.
The x-intercepts are...
Okay, so one way is if we factor this, we get x plus 3 and x plus 1, which means that -1 right here and -3 are going to be intercepts, which pretty much means halfway in between is going to have to be -2. Right? Okay? And if we put -2 back in, either the standard form or the factored form, what does that give us for a y? A -1. We've got a vertex about like that. So we've got a parabola that does something like this, right? Okay? Now, if you're graphing it this way, what you are really graphing here is this. Instead of a 0 being in that spot, you're assuming that there's a y in that spot, so that you have 2 variables, and then you graph it on a 2-axis graph. Okay? But that's not entirely a bad thing to do. Now, what you don't want to do at this point is the shading. Okay? Because the shading really doesn't imply that it's y values that we're interested in, and it's not. What we're interested in is a single value, x, and how that relates to 0. Okay? So instead, what we're trying to say is, on this graph, on this parabola I drew, for what x values do I have answers that are less than 0? Okay? So that's why on the answer sheet, you only saw the number line. Because even if I do this, all I'm actually really interested in are the x values that this is happening at. Oh, I have to redraw a few lines there. I don't care what's going on with y because I don't actually have a y. I really only have x values. And that x-axis, that number line, represents the 0. So I'm basically asking, when does this graph end up below 0? So the first thing we have to make sure we understand is, where does it change? Where does the graph go from being above to being below?
At the x-intercept.
At the x-intercepts. So here at 3, negative 3, and here at negative 1 is where I actually have the x-intercepts, which come from the factors of the quadratic that I started with. And those points are important because those are the points where my graph changes from being greater than to less than, from being above to below, and vice versa. So if I know where those points are, then I can test in between those points to see when do I get answers that are above or greater than 0, and when do I get answers that are below or less than 0. Okay? Excuse me. So if you hadn't done the whole two-dimensional graph, what you saw on the paper was factor first, identify those x-intercepts, and then on a number line, since I'm only really interested in x values, I'm going to make 2 tick marks that represent that negative 3 and that negative 1. And then since I haven't gone through the process of actually drawing the entire parabola, what I just need to know is, what kind of answers do I get here? Are they going to be greater than or less than 0? And then what kind of answers am I going to get in between? And then what kind of answers am I going to get out here on this end? And so the way to test that is to just pick test points in each of those sections. So a value that is less than negative 3, okay, how about a negative 4? It could be a negative 5, it could be a negative 10. It doesn't matter what it is, it's just something in that section. Then I need a value that's between negative 3 and negative 1. Well, negative 2 seems easiest because anything else would have to be a decimal or a fraction. And then I'm going to pick something that's out here bigger than negative 1, and so I picked 0, because 0 is always easy. Okay? And so now I'm just going to decide. If I put negative 4 in here, I don't even actually care what the actual answer is. What do I really care about? Is it positive or negative? Is it going to be bigger than 0 or less than 0? So that's the little plus and minus signs you saw in there. When I put negative 4 into this factor, do I get a positive or a negative? A negative. When I put negative 4 into this factor, do I get a positive or a negative? What happens when I take a negative times a negative? We get a positive overall. So this section gives us positive answers. I don't care what the actual answer is. As long as I'm comparing to 0, I just want to know, do I get positives or negatives? With me? Okay. How about negative 2? Is that going to give me positive or negative? How about this factor? So what's a positive times a negative? It's a negative overall. So that section is going to give me negative answers. How about 0? Positive. Positive. So overall, it's going to be positive. Now, what was I actually looking for? I'm looking for answers that are less than 0. So do I want the positives or the negatives? I want the negatives. I want this section right here. Okay. Now, what about these endpoints? Should I include them or not?
No.
No, why not?
Because it's not equal to.
Because of that inequality sign. If it's not equal to, then it's technically the open circles, and that's why parentheses negative 3 to negative 1 is the final answer. Because I do not want to include those endpoints. Okay, so it's not just about coming up with the negative 3 and the negative 1 and then saying, oh, so x has to be, less than negative 3 and x has to be less than negative 1. It doesn't work that way when you get beyond linears. So, those of you who did the two-dimensional thing, you didn't necessarily do it wrong. You just did a bit more than what was actually necessary. But your idea behind it was still pretty solid. The idea that we're going to make this parabola and we're going to figure out when is my parabola above the axis in positive answers and when is it going to be below the axis giving me negative answers. But you can actually do that on just a single number line since it's really only x that we're interested in. We're not really interested in y values. Does that make sense? Questions on that? Yeah.
For each section, is it always like opposite of the previous section? Like for negative one, that was positive, so the next one is past the negative.
With a quadratic, usually, the only time that that doesn't happen is if you only have like one x-intercept because it's actually the vertex, and so then both sides could be the same thing. But if you actually have these three sections, it usually, yes, will go positive, negative, positive,
So
or negative, positive, negative.
One side of test.
As long as it's quadratic. Now you get beyond quadratic, all kinds of funky stuff starts happening. So you're better off actually testing each section to be sure. But quadratic, yes, it's almost always alternating. Any other questions on this one? Okay. So then your second inequality was a rational. This is where things get a little funky. So the first thing we need to do here is what?
Move the 1 over.
Move the 1 over, because we always want to be comparing to 0. Right? When we draw that number line represents 0, and that's what we want to compare to. Are we above or below? Are we positive or negative? Okay? So whether it's quadratic, rational, whatever it is, we're always going to want to bring everything over to one side and compare to 0. So that's our first step here, is to make it x over x minus 2, and then subtract the 1 and make that greater than or equal to 0. Okay? And then if it's rational, we want it to be a single rational. So that's why you saw in the paper that the next step was to combine these two and get just one fraction. Okay? Which means that I need to change my 1 into an x minus 2 over x minus 2 so that I have the common denominator. Okay, so now my common denominator is going to be an x minus 2. And what's my numerator going to be? Positive 2, because the x minus x cancels out, and it's still a minus negative 2, so it should be a positive 2 on top. So this is really the rational that I'm interested in. And how does that compare to 0? Okay? All right, so go back to thinking about the graph of this for a second. We kind of do the same thing for a minute, and we say, well, let's replace that with y for just a second. Do I have a vertical asymptote? Where?
X equals
At 2. 1, 2. Wow, that got really nasty, really fast. Try that again. There are all kinds of lines going on. There we go. So net, 2, 1. There we go. Okay. Do I have an end behavior asymptote?
It's 0.
It's at 0, right? Top degree is smaller than bottom degree. That's going to be a 0. Okay. Do I have an x-intercept? No, because my numerator is just 2. If I set that equal to 0, nothing's going to happen. Do I have a y-intercept? -1. Okay, so it's going to look something like this, and then something like this. So in this case, where did things change? Where did my graph change from being below the x-axis, my 0 line, to being above the x-axis?
2, 4, 2.
At the 2. Where did the 2 come from?
Okay.
The vertical asymptote.
It was the vertical asymptote that came from the denominator. So, when you are dealing with rationals, in addition to what the zeros are, the x-intercepts, which in this case we didn't have any. But if you had an x minus 2 on the top, well not x minus, x plus 2 on the top, okay, then you would want to look at both the zeros that you get from the numerator and the undefined values you get from the denominator. Okay, those values where we would put vertical asymptotes. And then go through the same process. So now we're going back to this actually just being 0. Right, so back to just comparing to 0. So on my number line now, I have tick marks for zeros and undefined values. In this case, there were no zeros, there were no x-intercepts, so it's just the undefined value that's going to get labeled. And will 2 be included or not included? Not included. Undefined values are always not included, even if that says or equal to. 0 values, on the other hand, x-intercept values, would be included in this case because of the equal to. But I didn't have any x-intercepts. Okay? But undefined values, no matter what the inequality sign says, always not included because they're undefined. So now, if I test something over here, like 0, and I test something over here, like maybe a 3, what happens when I put 0 in here? I get -1, so it's going to be negative. What happens when I put 3 in here?
Positive.
It's going to be positive. Which one do I want? The positive. I want answers from this to be greater than or equal to 0. So the section I want is this section. And how do we write that in interval notation?
Parentheses 2, infinity.
Okay? Now, just as an example, just to make sure you understand what I'm talking about. What if, on the other hand, we ended up with x plus 2 over x minus 2? Okay? I still have a vertical asymptote at 2. But now, where's my x-intercept? -2. So I'm now going to have 2 tick marks because I had an x-intercept at -2 and a vertical asymptote that was going to be at 2. So -2 gets labeled here, +2 gets labeled there. Will -2 be included or not included? Included. As an x-intercept, if we have our equal to, that's going to be included. Will +2 be included or not included? Not, because as the vertical asymptote, it can never be included. Okay? Then we test. So, -3 in the top would be positive or negative? Negative. -3 in the bottom, positive or negative? Negative. What happens if I take a negative over a negative? I get a positive overall. Okay, again, as long as we're comparing to 0, I don't care what the actual answer is, I just care if it's above or below, positive or negative. Put in 0, top's going to be positive, bottom's going to be negative, and so positive over negative is negative overall. Put in positive 3, numerator,
Positive.
denominator, positive over positive, what do I want? The positives. So I want this section, and I want this section. So how do I write that in interval notation?
Infinity.
Say again?
Infinity.
Negative infinity
-2 bracket.
to -2, bracket to include that one, union,
Parentheses 2.
parentheses 2 to infinity.
Why is the positive 2 parentheses even?
Because it's unequal.
Because the positive 2 is coming from the undefined value, the vertical
Oh.
asymptote. So we can never use anything that's coming from the vertical asymptote.
Okay.
Doesn't matter what your inequality sign says.
Okay.
Okay? So we can never include the undefined values, the vertical asymptote values. But our 0 values, our x-intercept values, will depend on whatever our inequality says. Okay, does that make sense? So the basic idea is the same with rationals as it was with polynomials. We're still finding where's the change going to happen, and then test each section to see which section gives me what I want. The difference with rationals is that we have to make sure we understand which of our numbers are coming from zeros, from x-intercepts, and which of our numbers are coming from undefined values or vertical asymptotes, to make sure that we never include those undefined values. And then we use the inequality to decide about the zeros. Okay? Questions? All right, so we've got about 10 minutes, a little bit more than 10 minutes. So you got a little bit of time that you can go to some of the rational and inequality problems that were suggested on the checklist. Work a couple of those out before you leave. Remember Friday, those of you who are going to be here, please bring your earbuds and your Inspire booklet, okay, because the lesson you're going to get on Friday is just on video, on Canvas. So you're going to want to be able to listen to that. You're going to be taking notes, and it's over the application sheet of the pretest. So along with just showing you how to do the problem, I'm also going to show you how to use the calculator to help you. So you might want to take some notes in your Inspire booklet. Those of you who are not going to be here Friday, the video is up. Okay, it's on Canvas, it's ready to be accessed, so if you want to do it ahead of time so you don't have to worry about it over the weekend, it is there for you to access. Okay? Tuesday will be our post-test. Okay, so Monday is our last day of review. Tuesday will be the post-test over our Chapter 2 material. We'll have a few minutes at the beginning of class on Tuesday before we start the test. So if you have a few last-minute questions, we can try to address them then quick. But it'll only be 15-20 minutes. So if you have a major question, email me, and we'll try to set up a time before Tuesday to get together. Okay? All right, we got a few minutes. Get to work.